Hi guys, welcome to chapter 9. So we're almost done. I know you guys must be feeling fatigue. I know we've been going on for quite some time now. But so for chapter 9 we'll be looking at the failure criteria example. Okay? So um, in this section we'll be looking at results from a mechanistic pavement analysis and comparing them to the empirically derived failure models to determine the pavement life in terms of load failure. Okay? So the controlling mechanism for this example is obviously the failure loads. That's the controlling mechanism, right? And various thicknesses of an HMA, which is hot mix asphalt, were plotted against and computed or plotted against the computed number of repetitions of failure for 150, 250, and 350 millimeter like granular bases, right? And the controlling criteria in the design is the one requiring the greater thickness of the surface material for a given traffic level, right? And keep in mind that these charts, they're just developed for holding the material properties constant, and they're not to be used in any design. So this was just so that we can see how they behave. Okay, so the pavement design resulting from the three traffic levels, right? So the arrows in the graph, the graphs on the next slide, right, are given, right, above the graph. You'll see them there above, like on the graph itself, right? From the example, like in the tables, so our previous example, the resulting thickness of asphalt were rounded up from 12.5, and the assumed minimum thickness from the HMA layer was 50 from the example we had for flexible pavement, for the flexible pavement design, right? Note that the writing criterion controlled the design in all cases except for those involving thicker two pavement sections of 2 million load repetitions, right? The choice of which of the three equivalent pavement designs to use at any of the traffic levels would depend on the life cycle cost analysis, right? Remember I was talking about life cycle cost, and you must always talk to your client about life cycle cost and life cycle cost analysis, because it's very important, because that's the objective what we're trying to reach. We're trying to actually build something, so we need to look at the life cycle cost, right? And finally, for the 2 million load repetitions, the granular base thickness, right, has less impact on the HMA thickness, of course. Okay, so yeah, let's move on and let me show you guys what the graphs look like. Okay, so this is the design chart example for 150 millimeter. Okay, so for 150 millimeter, we're looking at, that's at 40 kilonewton loads. This is the thickness, and this is the thickness. So we're looking at rating will start, if you go, that's what, 4 to the power 10. Okay, so this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So here in between here there's 10. So here there's 1,000. Between here there's 1,000. 1,000 divided by 10. So that's 100 each, right? So here it's going to be 4 to the power 10 plus the 100 that you have here. We're saying that at a thickness of 100 millimeters, rating will happen, right? The rating starts, right? And then here you can see we're saying at 1, 2, 3, 4, 5, 6, 7, it looks like 8. So for 10 to the power 4 plus 800, at this point, this is when fatigue starts. As you can see from the arrows here, the red arrows showing each point. So we know at what thickness. So at the thickness, we see exactly how the fatigue behaves, like how the rating behaves in relative to the fatigue. So we're expecting fatigue failure somewhere up here, closer to 10, as we're moving closer to 10 to the power 7, which is conclusive with our results, and conclusive with you can see here E1, E2, E3. This we got these from the calculation. So this is confused. So this would be a typical design chart for example pavement. So depending on the load you have, you can then calculate to see what thickness you require and if any rating will occur. So this is how you'd be using these design charts. But remember, these are just an example, so you can draw your own charts from the results, and then you can use them, and then they're using them as an example. So in essence, what we're trying to get at here is, when you guys were looking at all those design charts that I showed you previously, or all the design charts that you guys will look at, that is how they got to it. They did an experiment, they found the data, then they plotted it out, and now we use that as an empirical method of finding our thicknesses. So this is how empirical methods are born. in a sense. So I'm trying to show you the inception, or I'm trying to say you to be able to conceptualize how we use the empirical method. So yeah, let's move on. 250 millimeter base. So this graph shows the design chart using the 250 millimeter base. Kind of the same thing. You can see it's going to be your force, your load against your thickness. So yeah, and you can see you can pick up various points depending on the strain. So 500 psi there, 750 there, and 7,500 there. So you can you can really see where's where, and then you can know exactly what's going on. E1, E2, and E3, how they'll vary with the graph. Anyhow, let's move on. 350, I'm sure you can see that it's a bit different. So you can see that the rutting has moved further because it's thicker, so there's less likely to be rutting, so it's thicker, so it's less likely to be affected by rutting because it's got a thicker layer, so it can sustain a larger load before it begins to rut. It can even go through fatigue before rutting occurs on the surface because it's so thick. So you're just realizing how different thicknesses also relate to how the pavement will perform from an empirical standpoint. That's also what these graphs are showing. So these graphs have a lot of knowledge, there's a lot of application. I'm sure the more you look at them, the more you'll figure out things. I'm just pointing out things as we go through, and you see for different values. Here you can see that the 7,500 E3 does not even apply anymore. We're only applying E1 and E2. So those are the only two compression strengths that we would be worried about, or forces that we would be worried about, as in pressure wise, the PSIs would be worried about, or the loads. Let me see, these are the only two loads would be worried about, and you won't even get fatigue. You don't be fatigued here. There will be no fatigue. You might only start to get rutting, but it's minimal, and there'll be no fatigue at all. Fatigue will only happen when you put on the maximum load, which is 3,450 megapascals. So you can see the thicker you have it, the stronger it'll be, and it'll perform better also. Okay, let's move on from that. So here now we get to compare the results from using a base thickness, the granular base thickness, and having an HMM thickness. So you can see here the rutting, and fatigue. So we can see here the different results from our graph. We'll comparing the example designs. As you can see here, the thickness of HMA varies a lot. So what you can see here is that even we've maintained these base thicknesses of 150, 250, and 350, right? So here you can see that you will most definitely, for lower force, you most definitely need less HMA thicknesses, right? But then when the force goes up to 2 times 10.5, right? You then have 150. You see how the HMA needs to become thicker, right? And then when it's extreme, you can see it's still performing the same way, right? So this then comes that cost benefit analysis. Is it better to, if and also where you are on site, is the aggregate available? Can you have enough aggregate to have that 350 base? If you can have aggregate to have that 350 base, and which means you won't need an HMA thickness of 190, it's better to have this thick 350 base and have maybe an HMA of 50, and your subgrade is 350 thick, because that will save you money, because hot mix asphalt is more expensive to procure. It's more expensive to place on the road than finding aggregate. That also depends, is the place you are, is aggregate available? Because for example, like in New Zealand, where I am in the East Coast, in Gisborne, aggregate, there was a time when aggregate was really hard to come by because of the cyclones that washed away a lot of bridges. So there was no aggregate. So in that case, aggregate is hard to come by and the bridges aren't fixed, and maybe it'll take a few years to fix the bridges. You would then rather spend your money on the asphalt. Then maybe you would try and balance it out. So where you would have, instead of having a 350 mil thick gravel layer, you'd maybe try and make it maybe 200, right, or 250, and then your asphalt doesn't have to be as thick, you know. Like you try and manage your asphalt thickness. You know, you mix and match, in a sense. You mix and match. But you know, if you have more aggregate, most definitely, and it's cheaper and it's available, you can go for it. So this is just showing you the different situations, or in comparison, of how base thickness and HMA thickness would react for various load scenarios or various loading scenarios. So this is very important because you can use this to kind of rationalize your design and try and optimize your design. Like I've been saying, design optimization is very important. You need to focus on design optimization. That's the difference between an engineer and a good engineer. So design optimization. So in essence, what I was trying to show you guys here is, I was trying to get to this to show you how you can mix and match different options and try and see how you can optimize your design. Okay, so yeah, I think that is all for chapter number 9. Let's move on to our last chapter, which is chapter number 10. I'll see you there.